Let's continue talking about voting system criteria. These are fairness criteria, and just to refresh our memory about what we did last time, the sort of big idea, and I hope you will put this chart in your notes somewhere. You might want to put it on its own page because we're going to be adding onto this as we go along. We have our 4 voting systems that we've discussed so far. Actually, we are going to add on at least one more voting system. There are others. These are just 4 that we've talked about. And then we have various criteria. And the first one, the only one that we've talked about so far, is the majority criterion. And remember, the majority criterion means in this or that system, it means if somebody actually is ranked first place by a majority of the voters, then they should win the election. And last time we discussed, that actually is true of the, so this is going to be like a big table. That actually is true of the plurality and the Condorcet, but it is not true of the Borda. And we didn't talk about whether it's true or not of the ranked choice. I'm going to say, just for the sake of having this in your notes, I'm going to put a check here even though we didn't talk about this, and this is actually going to be on the next homework assignment. So I don't want to get into that just because I want you all to think about it on the next homework assignment, but there should be a check there also. All right? So the idea here is there are many ways that you could try to say if a particular system is good or not. There are many different ways that you could try to evaluate the systems, and this is one way, this majority thing. And in this particular sense, these 3 are kind of good, and the Borda is kind of bad. All right. This doesn't mean Borda is total garbage, because we're going to have several other ways of evaluating these, and you're going to see some checks and some X's and O's. All right. This is where we're going with this. So let's talk about another criterion that I want to discuss. This one is another fairly, it's kind of similar to the majority, but it's a little bit more extreme. This is called the unanimity criterion. The unanimity. Unanimity is a version of the word unanimous. This is about if all the voters happen to agree, which of course in real life this doesn't often happen, but if all the voters happen to agree, then obviously the person they agree about should be treated appropriately by the voting system. So it says, this is, let me just say informally first of all, this is about when all the voters agree. Then the result should also agree with them, right? The unanimity criterion. Like I said, in real life, usually all the voters don't agree. But certainly, if they did, the system better do what they say if all of the voters actually agree about their opinions about something or other. All right? To be specific about how the unanimity criterion is written, so specifically, I'll give you the real definition here. We say a system satisfies the unanimity, satisfies for some reason in my experience teaching this class, this seems to be a hard word for some people. The word is unanimity. A lot of people write like unanimity or umity. It's unanimity. A system satisfies the unanimity criterion. This is a real definition now. When, if all the voters agree, I'll say if all voters rank, let's say, X above Y, then Who should win? X? Yeah, this is the natural thing. Although actually that was a bit of a trick question. I'm not going to say then X should win, although that is the natural thing. What I'm going to say instead is slightly different, but it's an important distinction. Then Y should not win. All right? If all the voters rank X above Y, then Y should not be the winner. This is the unanimity criterion. This is a very kind of low bar for being a fair system, in my opinion. Certainly, if everybody thinks X is better than Y, Y definitely should not be the winner. All right? Why does it say Y should not win rather than, I will just say, this is a note, it doesn't say that X should win. Since the reason why is because if all voters like X better than Y, that doesn't actually necessarily mean that X is the best overall. It just means that X is better than Y. There could be there could be like another Z who's even better than X, all right? And in that case, certainly X should not win. All it means, though, is that Y should not be the winner. So it doesn't say that X should win since the voters may like somebody else even more. Right? Just because X is always above Y, it doesn't mean X should be the winner. It just means that Y definitely should not be the winner. That's what it does mean. The voters may like somebody else even more. Right? All it says is that Y should not be the winner. All right? This is called the unanimity criterion. And I want to talk about our 4 different systems that we have discussed so far. Which of them satisfy or do not satisfy the unanimity criterion? I would say this is a very basic thing that any reasonable system hopefully would satisfy this property. You shouldn't, in my opinion, you wouldn't want to use a system in real life where you could have somebody who's ranked below somebody else by every voter and they end up winning the election. That would be a very weird outcome. We don't want that to happen in real life. All right, what about our various systems? Let's talk about plurality. So which of our systems satisfy this unanimity? Let's talk about plurality. Any thoughts about this? If you're using the plurality system and everybody likes, the plurality system is like how we do ordinary voting in our real politics. Is it actually true that if everybody likes somebody more than someone else, then the somebody else can never win the election? I think this really is true in real life ordinary voting. If it's between Harris and Trump, and by some miracle everybody actually agreed that Trump is better, then Trump is going to win, right? There's no way there's nothing weird that can happen when you do the math, whereby someone who everybody dislikes ends up winning the election. All right, so which of our systems, plurality, does satisfy this? We need to write a little proof though, and this is very similar to the ones we were doing last time. Again, the proofs for these all have a standard structure. You basically just have to fill in the details in the middle. So I would like to write a proof of this. So maybe I'll just write very clearly what we're trying to prove here. Plurality does satisfy the unanimity criterion. Unanimity crit. Here's my proof. All right. Again, the structure of these little proofs that you're going to write is always the same in each different example. It amounts to saying you sort of imagine a certain scenario. Now, in the case of the majority criterion proof, we began by saying something like, imagine that X is ranked in the first place by a majority of the voters. Now, the unanimity is not about that. The unanimity is about this. If all voters rank X above Y. So we begin by saying, imagine all voters rank X above Y. Now, of course, you don't have to write exactly the same words that I'm writing, but I think it can be helpful to have a structure in place. You can rephrase this in your own words if you like. You start by imagining that all voters rank X above Y. You say something, 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 and your conclusion should be, thus, Y does not win. Remember, that's what the unanimity criterion says. It says if all voters rank X above Y. What? I don't know what that means. Disable it. I don't know what that means. Thus, Y does not win. The unanimity criterion says if everybody puts X above Y, then Y should not win. So that's what you need to demonstrate in your little proof here. And of course, what you fill in the middle here is probably just one sentence or so, but it should be specific, in this case, to the plurality, right? When you explain why Y is not the winner, you have to say something specifically about the plurality system. Anybody think you can fill in the blanks here? Imagine that all voters rank X above Y. According to how the plurality system works, can you explain why this automatically means that Y doesn't win? You could imagine, you could imagine like in real life, if actually every voter likes Trump better than Harris, why does that mean that Harris will not win? Because she doesn't get any votes, right? That's what I would say. And specific to the plurality system is only about the first place rankings. But anyway, if all the voters rank X above Y, Y gets no first place rankings, right? Because everybody's going to put X above. So imagine all voters rank X above Y, then Y gets no votes ranked first, right? And thus, Y does not win. I should maybe say, using the plurality system, of course. That's my fill in the blanks. There are many other ways you could say the same thing, but what you say probably needs to mention first place rankings because that's what the plurality system is all about. It's about how many first place rankings did you get, all right? And if everybody likes X better than Y, then Y gets no first place rankings at all. That's how we do it. Can we talk about the ranked choice? I would like you all to think about that. Do the same thing, but for ranked choice. So everything that you're going to write is basically the same, except for this one little thing in the middle. You will have to explain a little bit differently about, in the context of the ranked choice, which is about the rounds and people being eliminated. So let me just move on to maybe I'll add this into the big chart. You can scroll up. This is the unanimity. That's the next little column here. And we just described why plurality does satisfy the unanimity. All right, so this is another thumbs up for the plurality system. All you plurality lovers out there, this is good news for you. All right, let's try and do the same thing, but with ranked choice. So ranked choice voting, turns out, does satisfy unanimity. All right, and our proof has exactly the same structure. It's just that part in the middle which needs to be sort of customized for the ranked choice system. So the proof begins with, imagine that all voters rank X above Y. Something, something, something involving, so what you say in the middle here needs to mention somehow the rounds and the elimination, because that's what ranked choice is all about. And then you conclude, thus, Y does not win the election. All right, I'll give you a moment to think about this. You can chat with your friends about it if you like. You have to imagine what would happen in a ranked choice if all the voters ranked X above Y. explain why this means Y doesn't win the election. I hope it's not too early in the morning for abstract thinking. It's never too early. To say something about the rounds and the eliminations. Y does not win. I'm going to see if I like your one sentence. Yeah, I like that. How's it going? All right. Anything? This is the one where you eliminate them one at a time. How's it going? Which I think you can be more specific. Which round of right? Get anywhere? All right. You're ready to fill in the blank. How's it going? Maybe you're thinking of the Condorcet method, where there's a bunch of like one-on-ones. Sounds like that's what you're talking about. Whoever has the least in the first round gets eliminated. All right, let's talk about these. I didn't walk around to everybody. I hope you don't mind. I saw a lot of people saying good things. You have to say something about the eliminations, and the basic idea is if everybody likes X better than Y, then Y is going to be eliminated at some point, right? Certainly, like Y cannot beat X, so Y will be eliminated in one of the rounds. I think you can even be more specific, like when is Y going to be eliminated?
Before X.
Yeah, well, yeah, certainly Y will be eliminated before X. I think you can even say for sure Y should be eliminated in the very first round because they're not going to get any votes in the top position in the first round, right? Because X is always above Y. And the way you do the rank choice is by counting up the first position rankings in each round. So Y actually will be eliminated immediately. They're never put on top because X is always above them. So that's what I'm going to say. Y gets eliminated in the first round since Y gets no first place rankings. That's because X is always above Y in all of the voters' rankings. And so Y can't get any first place rankings. And thus, Y does not win the election because they were eliminated in the very first round. All right? Anybody say something slightly different and you're wondering, I mean, like when you're doing this on the homeworks or on the tests or whatever, of course you don't have to say exactly the same words that I am saying, but you have to say something appropriate. All right, great. So this ranked choice is a check in the unanimity column. I'll stick that in my chart here. Ranked choice does satisfy the unanimity. The other two, the Condorcet and the Borda, again, I'm going to leave those for you guys to do on the homework, but just spoiler alert, they are also check marks for the unanimity criterion. All right. Actually, all of these systems satisfy the unanimity. The unanimity is such a sort of, I would say, low bar for fairness. It would be truly absurd for a system to not satisfy the unanimity criterion. It's such a low bar that you might feel like, well, what's the point of even talking about it if basically every reasonable system satisfies this? This is the kind of thing that mathematicians actually like to talk about sometimes. Stupid things, kind of like the number 0. Like, what is the number 0? Kind of doesn't mean anything, but it is important in a lot of abstract settings to talk about it. And it's kind of the same way. Like, this is kind of a very, very easy property to be satisfied by a normal system, but it's for that reason it's a good thing to discuss. All right. Great. Something that somebody always asks me, before our tests. By the way, I believe our first test is next week. Can you believe it? That's because my plan for the semester was to have like kind of a lot of tests, just because of the way that the somewhat strange way that the tests are being graded. People always ask me, should we memorize this whole chart? And my answer is no. I wouldn't say that you should memorize the chart. But I would ask you, like on the test, I might ask you, one of the things on the big checklist is the unanimity criterion, and I might say, show me a proof that Borda satisfies the unanimity. So you don't need to have that memorized. You need to be able to reconstruct the reasons why. All right, but we can talk more about that when it's closer to the test time. All right, this is the unanimity criterion. We ready for another one? Another criterion. I have several more of these criteria. That's the plural. How about another one? This is called the Condorcet winner criterion. And I'm going to write, just because that's a little too much to write, CWC means the Condorcet winner criterion. Of course, we have a system called Condorcet's method, which looks for the Condorcet winner and chooses them to win the election. But you could also ask about the other methods and do they respect Condorcet winners in the appropriate way. So maybe I'll just refresh our memory. So this is, recall a Condorcet winner. There's some business about this on the homework that's due today. A Condorcet winner is one who would win every one-on-one comparison, right? That if somebody is a Condorcet winner, then if somebody wins every one-on-one comparison, then they're called a Condorcet winner. Of course, in real life, this doesn't mean they automatically win the election. It just means we just call them a Condorcet winner, all right? But the Condorcet winner criterion says a system is good if this person also becomes the winner of the election, all right? If somebody would win every one-on-one comparison, that should make them win the election. So that's the Condorcet winner criterion. So I will write that formally. A system satisfies the Condorcet winner criterion when, if there is a Condorcet winner, of course in typical examples often there is no Condorcet winner, but if there is a Condorcet winner, then they win the election. Right. This is called the Condorcet winner criterion. All right, if there is a Condorcet winner, then they automatically win the election. That's called the Condorcet winner criterion. All right, so you can put that in your little chart. This is another column, the Condorcet winner criterion, and we kind of get one check mark in the column for free here. Is the Condorcet method definitely does satisfy that. That's the whole purpose of the Condorcet method. Is if there's a Condorcet winner, you make them the winner of the election. That's how the method works. Although the others, it's something to talk about, but there's really not much to say at all about the Condorcet method and the Condorcet winner criterion. The Condorcet method, the whole method just says you find the Condorcet winner and then they win the election. But the other ones is a little more interesting to talk about. What about the plurality? Anybody have any thoughts about this? Is it true that when you're using the plurality system, which is, again, like sort of the normal system that we use for voting typically in our politics, is it guaranteed that the Condorcet winner always wins the election? That's the question that if it's going to be a check or a X here. Anybody have any thoughts about that? Is it a guarantee that the Condorcet winner is going to win the election? I see some people slightly shaking their heads. I think the answer is no. I'm going to put an X here. Remember, if the answer is no, it means you need to come up with an example showing a situation. Was there ever a time when there was a Condorcet winner but they ended up losing the election? Does anyone remember? We have actually talked about this before. Yeah?
In Bush-Gore-Nader.
Yeah, in the Bush-Gore-Nader election, if you recall, in the sort of the thing that's interesting about that election was that if you had considered only Gore versus Bush, then Gore would have won. And also, of course, if you had only considered Gore versus Nader, then Gore would have won, because Nader was the weirdo outsider. So in that case, the plurality, there was a Condorcet winner. It was Gore. So I'm going to write this down here. So I'm going to say the plurality does not satisfy the Condorcet winner criterion. Remember, if you are saying something does not satisfy one of these, you need to demonstrate with a counterexample. And a counterexample, I mean, you could just try to make up your own example, which is sometimes difficult, though. A counterexample would be the Bush-Gore-Nader election, which we've talked about several times. And in that election, Gore was the Condorcet winner. But Bush won the election. So this is an example where plurality sometimes can make a Condorcet winner lose the election. And that's why there's an X on the chart in that spot. The plurality system can sometimes make a Condorcet winner lose the election. In that case, Gore was the Condorcet winner, but Gore ended up losing the election. All right? And so this is why the plurality system does not satisfy the Condorcet winner criterion. All right? What about, let's talk about the rank choice. It turns out actually the ranked choice voting also does not satisfy the Condorcet winner criterion. We're getting pretty thick with the jargon and the acronyms. We are now at the point where somebody walking into class off the street will not have any idea what I'm talking about. I hope that you all are keeping up with it. That's how you know you're doing some real math. The ranked choice system does not satisfy the Condorcet winner criterion. We have also seen examples of this. Actually, if you've done the homework for today, you will have seen an example. Anyone who looked at the homework know what I'm referring to? There is actually an example of a ranked choice election where there was a Condorcet winner who ended up losing the election. Anyone remember? What is? Some of you are nodding. When did that happen? It has happened. It can happen. Yeah?
There's a tie.
It doesn't really have to do with ties. Anyone know what I'm referring to? This was in the homework for today. Yeah?
It was baggage.
Yeah, it was baggage, she said. Yeah, this is like something you should tattoo on your arm if you're really into this. If you're a real ranked choice hater. It was baggage. He was the Condorcet winner in that election, but because they used the ranked choice, he ended up losing. The Peltola won the election. So the ranked choice also does not satisfy the Condorcet winner. I will say, for example, because this is what is necessary, you need to demonstrate an example. For example, in the Peltola, Palin, Begich, which used ranked choice, Begich was the Condorcet winner. We didn't specifically talk about this in class, but it's one of the homework problems for tonight is to show that Begich was the Condorcet winner. So it's true. Begich was the Condorcet winner. But Peltola won. And this, as I said in class last week at some point, this is really a good reason to be a ranked choice hater. I'm not a ranked choice hater, but there are reasons why people might be suspicious of the system. And in my opinion, this is a valid objection to this system in this particular event. Begich was the Condorcet winner. That means, in particular, remember that means you would win in any one-on-one comparison. So in particular, it means that Begich, the people of Alaska actually liked Begich better than Peltola. But Peltola ended up winning the election. This, in my opinion, is messed up. Now, it may not be. I'll leave it to you to decide, does this mean that ranked choice as a whole is garbage? I will say, the same exact thing can happen with the plurality system. So if you're prepared to be a ranked choice hater because of this, you should also be a plurality system hater. Like, it's not worse than plurality in this sense, but it is. There is something weird about this. All right, so X in the ranked choice column, I got an X here, all right? And what about the Borda? Now, the Borda, we haven't talked about specific real-life examples of the Borda because the Borda is not typically used in real-life politics for reasons which we're going to get into eventually. The Borda, though, does have an X here, and for this, we're just going to have to use like a made-up example. But I think actually we have already talked about the appropriate made-up example. So, sorry to keep on scrolling up and down. There should be an X in the Borda row for the Condorcet winner criterion. So Borda also does not satisfy the Condorcet winner criterion. And the reason is because, so an example, you have to give a counterexample in order to demonstrate that it does not satisfy. And an example you can use is from class last time, and actually several times before that also. There's kind of like a big recurring example. We did it at the very beginning of class last time. There's a big example that we did, which started like 14 people say A, B, C, D, 10 people said whatever. I don't want to write all the details, but I hope you remember what I'm talking about. This was a big example that we've done all of our different methods on. And in this example, in that one, I will just have you remember, the plurality system chose A, the ranked choice chose D as the winner, the Condorcet chose C as the winner, and the Borda chose B. And I said, like, the point of that example, the reason that we did that particular example, so many different methods, is just to show that all these different methods can give you different results. But what I would like to point out for the time being, why I bring this up again, is just because you can see here, C is the Condorcet winner, but if I use Borda, B wins. And that means the Borda does not always choose the Condorcet winner as the winner of the election. All right. So here, the important fact about this example for the purposes of Borda and the Condorcet criterion is that here, B wins with Borda, but C was the Condorcet winner. And so again, we have this situation where there was a Condorcet winner, but they end up losing the election in this case because of how the points add up. All right? So that means there's also an X in the Borda. Did I put it in there already? Sorry to scroll. Yes, I put it in there already. All right. This is what we got so far for our chart. Any questions about all of this? We got about 10 more minutes, which I think is enough time to talk about the next one that I'm going to put in the chart here. This is actually, so these three, in my opinion, are fairly straightforward. I don't know if you agree with me or not. I hope you're not too intimidated by writing these little proofs. It's not a big deal, although it does require some amount of thinking about it. Unlike adding up the points or something, it's a very different kind of mathematical skill that's necessary. Anyway, the next column the next criterion I want to talk about is a little bit more sophisticated, maybe, and it has a weird sounding name. I'll just abbreviate it here as mono. The next one we're going to talk about is called the monotonicity criterion. And this is a bit more sophisticated. But in my opinion, more interesting also. Monotonicity criterion. Monotonicity. So this is a fancy word that's used in a lot of different settings in math, this word monotonicity. Not really an ordinary word, but this is based on the word monotone, which people do use in real life. Monotone. And the word monotone, I mean, they say this like in music, or it generally means sort of, when you say somebody's like speaking in a monotone way, it means like the tone of their voice is not changing at all. It's just like boring and doing the same thing over and over again. The word monotone in mathematics generally means sort of like things go the same way. This is kind of the general sense of the word when it's used mathematically. Things go the same way. For instance, this is a true fact about my dear wife. When my dear wife goes to the grocery store, you gotta like walk through the store. She wants to walk through the store in a monotone way, meaning she starts at the front door, goes through the store, and ends up at the exit. She does not like to go back. If you forgot something, I gotta go back. That would not be monotone. So this is the way the word mathematically is used. Monotone means you just go sort of one way. You don't also go back sometimes. All right, things going the same way. The monotonicity criterion. So this is about. It is about sort of something about like moving or changing, which is what makes it a little strange to think about. But this is about. It's about how the system reacts if somebody changes their votes. All right. And this is another thing that's kind of sophisticated about this is that, of course, in a real life election, you're not allowed to change your vote. You vote and that's it. You can't say, oh, wait, I changed my mind. But if you're thinking about whether a system is mathematically sort of sane or not, or whether a system is fair or not, actually you can imagine scenarios where people are allowed to change their mind and see what would happen as a result of somebody changing their mind. So this is sort of, practically speaking, an unrealistic situation because in real life nobody's allowed to change their mind, but it still reveals real sort of truths about the mathematics of the situation. So anyway, the basic idea, I will say in this way, the idea, and I'll give a real definition next time, but in our remaining 7 minutes, we can just talk about the vague idea, and then I'll show an example demonstrating what I'm talking about. So the idea is, if I let's just say if I was going to put if I was going to rank A first, but instead decided to rank B first, then this sort of changing my mind, whether I did it in real life or not, even in my own head, this kind of changing my mind, this change. Now, in real life, big, large-scale politics, probably me, myself, changing my mind won't affect the results. But in a smaller situation, it could. This change, if anything, I'm saying I used to be putting A first, but I changed my mind to put B first, then this change should help B. And I'll say parenthetically, or have no effect. I mean, in real life, big elections, probably if one person changes their mind, it doesn't matter. But the idea is, if you are going to put A first, and instead you decide to put B first, this changing your mind should be beneficial to B, right? It would be crazy if somehow you were going to put A first, but then change your mind to B, and this somehow made A this somehow helped A. That wouldn't make any sense, right? So if I was going to rank A first, but instead decide to rank B first, then this change should help B, right? It's like if you're a Trump super fan and you try to convince me to vote for Trump, and I'm like, you know what? I like the sound of what you're saying. I'm going to change my mind and vote for Trump. In theory, that should actually help Trump, right? If for some reason that change of my mind ended up hurting Trump in the election, that would be messed up, right? This is what I'm trying to say here. All right, here is an example. So let's look specifically at an example here. How about if I just made up a real life example here. 5 people said A, B, C. 4 people said C, B, A. 3 people said B, C, A. And 1 person said B, A, C. All right? And let's try to think about this in terms of the Borda. So let's do this example using Borda, just as an example. All right? Now the points, the Borda is the one where you add up all the points. So the points in this election go 0, 1, 2. This is how the Borda points always work. It's 0 for last place and then going up from there. And then we add up the points. I hope you remember how to add up the Borda points. You always do sort of the number at the top of the column times the number of points in that position. So A gets 5 times 2 from the first column, 4 times 0 from the second column, 3 times 0 from the second column, the third column, and then 1 times 1 from the last column. This is 5 times 2 plus 1 times 1, which is 11. All right? B and C, I did this. I don't think we need to write out all the details. B gets 17 and C also gets 11. All right? And so here B is the winner using the Borda. All right? Now, I want to ask now, what would happen if somebody changed their mind? For example, and the changing of your mind in the specific case of the monotonicity, I want to ask specifically, what happens if we, this is how I'm going to describe this kind of a change. Boost the winner. What I mean by boost the winner is B was the winner, and I want to ask the question, what if some of the votes change by moving the winner up? What happens if we boost the winner? For example, e.g., if the CBA votes, that was in the second column there, 4 voters voted CBA. If the CBA voters change to BCA, they pushed the winner, the original winner, they pushed them up even higher in their rankings. What do you think? What's going to happen in this election if they made this change? Would B still be the winner, or would A or C suddenly become the winner after that kind of change? You could add up all the points if you like, although I don't think it's necessary by some kind of common sense here. What's going to happen? Who's the winner after this change will be made?
B.
B will still be the winner. Can you say why in terms of the points or whatever?
Because they got like lifted to first place.
Yeah, like if whatever happens in this case, B is just going to get more points than they used to get. And nobody else gets more points, like C is going to get less points. A will get the same amount of points. So if you think about it in terms of the points, if these voters change to this, then B just gets more points. So B still wins. And this is the kind of same direction that I was talking about, the monotonicity. If you boost up, if somebody was going to be the winner and you give them even more points, they still are the winner. This is the idea behind the monotonicity. And maybe I'll give you a little spoiler. For this exact reason, Borda, I'm going all the way up, Borda does satisfy the monotonicity. The monotonicity is about, what if we raise up the winner even more? The answer is they win even harder in the Borda system. All right? This is what we need to discuss for the others, though. I think that'll do. Let me know if you want to chat about the homework.